All right, ladies and gentlemen, class recording started. So, over the past couple days, we have been discussing how waves behave when they encounter other waves. And the one principle that kind of guides that is superposition, the fact that two waves can occupy the same place at the same time. And we talked about constructive interference, talked about destructive interference, and then yesterday we spent a good amount of time talking about, double slit interference, where we have diffraction and interference going on, and it gives us that distinctive pattern of constructive, destructive, constructive, destructive, constructive, destructive. While with the speakers it was loud and soft. If it was light, we would have certain spots that would show up. If we did this experiment here with two light waves, we would see that if we shined them against the wall or the screen, there'd be bright spots and dark spots and bright spots and dark spots along the way, because we'd have constructive interference of light, destructive interference of light. But it all deals with waves encountering one another. And we'll do a lab on this stuff next week, and we'll talk about how it relates to this equation, and where the bright spots show up and where the dark spots show up, etc., etc. So, waves interacting with other waves is superposition. But sometimes waves encounter matter. And that's really what physics is the study of how matter and energy interact. And so this picture right here illustrates the interaction of waves and matter, particularly light waves, but it happens with all kinds of waves. So this over here is what we refer to as the incident wave, or the incident ray. There's some source of light over here that's shining light in this direction. And then it encounters the boundary between two different types of media. So in this case here, it's going through air and then encounters glass. So there are three things that can happen when waves encounter a change in the medium. One is reflection. It can bounce off of that surface. One is refraction, where it enters that surface, but there's a change in certain properties of those waves, and we'll talk about what those changes are in just a second. And the third one, which you can't really see here, is absorption, where that medium can absorb the energy that is incident upon it and not give it back or let it pass through. And then it just absorbs that energy, and then the medium increases in energy, whether that be temperature or whatever it does then. Right? So, three things that could happen at this boundary: reflection, refraction, or absorption. Okay? So, let's first talk about reflection. Okay? So, here is more of a schematic drawing of what happens at that boundary. So, here's the incident ray. This was the one that's coming in. There's some source of light over here, right? And that ray is coming in this direction, and then this is the boundary. Okay? So, first, reflection. This is the reflected ray. Okay? Notice, theta 1, theta 1. Basic law of reflection. The angle of incidence equals the angle of reflection. So whatever angle this ray is coming into the boundary, it will bounce off of that boundary at the same angle. Generally speaking, we measure that angle at a line, or we measure that angle with respect to a line that is normal to the boundary, right? And normal is just a fancy word for saying perpendicular, okay? But if these two angles are the same, these two angles would be the same as well, because 90 degrees, we subtract, blah, blah, blah. But when we talk about the angle of incidence, we talk about how is that ray coming in, because it's an incident ray. So this is the angle of incidence, the angle at which it's approaching the boundary, theta 1. It bounces off the other side at theta 1 as well. Austin, go ahead.
So if someone were to hit a sound wave, you would make a sound wave. So say I used to do that.
Yep.
And then that wave comes and hits the board
Yep.
at, say, that angle.
Yep.
It's just going to bounce off, and it's going to, once it hits the board, then it's going to split into multiple ways. And they're going to go.
Now, the board, well, so the medium that the waves interact with determines which one or what percentage of those three things happen. Okay? So here, because this board is pretty solid,
Yeah.
it almost reflects everything that comes into it.
Okay.
Very little absorption, no refraction, because refraction involves passing from one medium into the other. This board doesn't let doesn't let things pass through it. Okay? So the nature of the material determines what happens or how much, what combination of those three things happen.
So the wave will, like, it's split, the waves, I always learned on it's the principle where the waves split the smaller waves.
Okay, that's going to be more how the wave travels, like from here to here to here to here. That's Huygens' principle, right?
Yeah.
So that doesn't necessarily affect what happens at that meeting point right there. That's more how it's traveling through a certain medium, but not necessarily how it reacts at the boundary between two different media. Okay?
So, like, every time the wave completes one cycle, then it kind of goes to smaller waves, and then they keep, but when they hit the board, they reflect at the same angle, they'll reflect at the opposite angle, and then say it hits another solid object, if it's just a room full of these boards and walls, if they're just going to keep going at the same angle and just keep bouncing.
It will keep bouncing off of whatever angle it approaches that surface. Yeah, and then because of damping, eventually the amplitude would die out, and then it wouldn't reflect anymore, because the damping is a case where energy is absorbed by the medium as it travels through. That happens at the boundary between two mediums as well, right? And so that can happen either as it's just traveling through one medium or when it encounters the boundary of another medium.
If you throw a tennis ball on a flat surface, it's just going to bounce at the same angle
Yep,
through it.
exactly, and that's the same thing with waves too. So, okay. Hey, good.
So what are the molecular properties that would determine whether a ray is reflected or refracted?
Wait, say that last part again.
Like a mirror and a window, like one will reflect one won't.
Yeah, it has to do with the molecular makeup of the substances, and more specifically, it has to do with reflection. It has to do with how smooth this surface is. Okay. At the molecular level, we think of this boundary as a straight line, but it's really not. At the molecular level, this boundary is like this and this and this and this and this and this, right? And so, but something like a mirror might be something like this, okay? Where here, materials will reflect off of that surface, but a ray that comes in like this is actually going to reflect this way, but then a ray that comes in like this will reflect this way, okay? We refer to this as diffuse reflection because it diffuses all the rays in all different directions. That's something like this board, because you can see like shape, but also too, it's white. And I think we know probably from somewhere along the way that things that appear white reflect light that comes off of it. Are we familiar with that concept that white light is really a combination of all different colors of light? Does that sound familiar along the way? But then people are like, well, wait a second. Doesn't a mirror reflect all of the light off of it? Yes, it does. But what happens is that, like, so this is yellow light, and this might be red light, and then this might be blue light, and the way that it all reflects, it all kind of mixes back together. There isn't a specific way that one reflects versus the other. But on a mirror, because the surface is relatively speaking flat, yellow will come in and reflect like this, red will come in and reflect like this, blue will come in and reflect like this, and they all sort of stay separate from one another. Does that make sense? Okay? Gotta look something up real quick. I want to know, I want to make sure I give you the right term. This one, this kind of reflection we call diffuse. This one we call specular. Okay? And that's sort of, they all obey the angle of incidence is equal to angle of reflection, but depending on how smooth, quote unquote, the surface is, that will determine whether it all kind of stays together or whether it just kind of like goes all over the place. A window, so what determines if this happens or if this happens has to deal with this concept that we call the refractive index. Okay? So the refractive index is, and that's, come up here. So, all right, where are we here? Edit. Okay, so the refractive index, which is this n value, okay, is a measure. Sorry, I jumped a couple slides because is a measure of how quickly the light or the wave, actually I shouldn't say just light because it happens with all waves, how quickly the wave travels through that substance versus the previous substance that it was in. So that determines whether it will bounce off or whether it will go through but at a different speed. Right? So if we think about it in terms of this, if you've ever if you cut the grass and you're on the edge of the grass between the sidewalk and the grass, you have like 2 wheels on the sidewalk but 2 wheels in the grass, it's sometimes hard to keep the lawnmower going straight because the wheels on the sidewalk want to roll more easily than the wheels in the grass do. So when you have different parts of the same object trying to travel at different speeds, we get this turning or this bending. And that's really what happens when a wave encounters a different medium. So here, it's a little hard to see here, so I'll highlight some stuff, okay? This spot right here is a boundary in that water tank, okay? And what happens, like the way that you do this experiment in a water tank is you actually put a piece of plastic in one part of the tank but not the other part of the tank, so the water is more shallow where the plastic is. Does that make any sense? Are you guys picturing that in your head? Okay. So yeah, like so if this is here, okay, if this is my water tank, okay, and let's try it. I'm going to try it. This is going to be an experiment. We'll see if this works. Hold on. Watch this. See if it works. Oh, that's not what I wanted to happen. I think I might have to draw like a solid shape with this blue line. Let me try that. Okay. Okay.
Draw like a rectangle using their, drawing rectangle tools.
Yeah.
Is that?
No. This one. Okay. Oh.
Isn't that supposed to be a rectangle?
Nope, this one's the rectangle.
Yeah.
So, alright. So, that, no. Yes.
Yeah, did the light.
Oh, I have to go dark blue for this one. Okay. So, there's a tank of water, side view. Okay, so we're looking at it from the side. And the way that that water tank works is you make waves like here by just like tapping the water, tap, 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 and then the waves travel through the water like this. Okay? But when you do the refraction experiment, you take a piece of plastic and drop it in the tank like there. And so then the waves are traveling through the water here and the water is this deep here, but it's only this deep here. Say again? Yeah, it's like a shoreline, which is also why waves break, because they're traveling through water, but if they can't complete a whole wavelength, they break onto the shore. So that's why waves break when they get to this, because this is what happens at the shoreline, right? The waves are in deep water, and then kind of gradually it gets shallower, but that's the same thing. So that change in depth is a change in the medium, that the wave isn't traveling through the same medium. Yes, it's water, but it's deeper water versus shallower water, and that causes a change in the properties of the medium, and that causes a change in the speed of the wave. Okay? So here you can see that this is the change in medium, and the waves here, all right, are coming in, and these are wave fronts, okay? And then these are wave fronts here, okay? And you can see that as it comes to this point here, that those waves, if you trace one here to here, or here to here, or here to here, when they encounter this boundary, one part of the wave starts traveling at a different speed than the other part of the wave starts traveling. And that's when we get the bending effect. But it really has to do with the change in medium and the change in speed. Okay? Are we okay with that idea? That change in speed is what we refer to, or how much the speed changes, we refer to as the refractive index. And so, we can see here in this one that it's kind of sideways, but we talk about an angle of incidence, but then we talk about a refraction angle. That's theta 2. So if we go back to this picture, here's theta 1, but then here's theta 2. And as you can see from the picture, there's a change in the path that that ray is traveling as it enters the new medium. So the property of this material, or the refractive index, determines whether it will let the ray pass through at a slower or faster speed, or whether it will bounce off of that surface because it can't pass through that material. That the molecular structure of that material doesn't allow the energy to be passed from one thing to the next, to the next, to the next. Because that's what waves depend on, right? You know, to travel through a medium, we got to transfer the energy from one to the next, to the next, to the next. Okay? Good there? You okay with that idea? So, generally speaking, not generally speaking, if we go from something that has a low index of refraction to a higher index of refraction, we see a bending towards the normal line. So in this case, theta 2 is smaller than theta 1. But in the other direction, if we go from a high, so this one here, we kind of assume that the ray is going this way, and then after it goes into the substance, then it's going this way. Okay? So if refractive index N2 is greater than N1, we bend towards the normal line. I'm good. No, because they're not, generally speaking, these two angles, theta 1 and theta, not generally speaking, theta 1 and theta 2 aren't going to be the same. These two angles are going to be different based on what that property of the second material called the refractive index. You see this in this example right here. Okay? You guys don't have this picture. I picked it up yesterday off of. So, all right. So, what? Your son. My son read Hatchet last year. Yeah. So here, okay, this comes in handy if you're ever diving for rings in the pool or spear fishing. So,
Spear fishing.
spear fishing, or maybe fly fishing if you
Bow and arrow fishing.
bow and arrow fishing.
Take it back to the Inuit style.
So here is an object on the bottom of the pool. Light from somewhere else over here goes into the water. The light bounces, well, I'll use red because that is, okay. The light bounces off of that substance, okay? And here, angle of incidence would equal angle of reflection because it's the same medium and we're bouncing off of an object, okay? So if we drew the normal line here, all right? Okay. So, Evan, like these two angles would be the same because we're reflecting in that case. Okay? But then this ray comes out here, 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 and then here is another normal line, and it's at the boundary between water and air. As you can see from this picture, the refractive index of water is 1.33. The refractive index of air is 1.0. So we're going from a higher refractive index to a lower refractive index. And as a result, in this case here, theta 2 is going to be less than theta 1. It bends away from the normal line. If we go from lower index to higher index, it bends towards the normal line. If we go from higher to lower, it bends away from the normal line. So then this ray comes out of the water in a different direction than it approached the boundary. Okay? But here's where that becomes an issue. Your eye receives that light that has refracted as it came out of the water. But your eye doesn't know whether light has been refracted or reflected. It just gets that ray and draws the line backwards. So here, I think we've kind of talked about this before, right? If that, okay, the hood, right? Fuad, if you look in the hood, can you see me? Okay. I can see you, Fuad, so just so you know, right? Maybe if the lights weren't on, it might help. But so if that was replaced with a mirror, right? I could see everything as it comes in, angle of incidence, angle of reflection, to me. If I didn't know you guys were sitting there, I would assume that that's where Fuad is, because my eye doesn't know that that light has been reflected. It's kind of like the thing with like a fun house or a haunted house or something like that, right? If there's like a mirror at the end of the hallway, someone could be standing around the corner, you would see their reflection in the mirror, but you don't know that they're standing around the corner, you just think that they're in front of you. Does that make sense? Are we? Okay. So. Okay, so let's do. We can do the fun house example. Yeah. So hallway, corner. Okay. So here's Austin. Okay. Here is Scary Monster. Okay. All right. You are not in the direct path of the light that's coming from the scary monster, right? Let's do this. We'll make it a little easier. Let's say that the monster has glowing eyes, okay? He has some scary yellow glowing eyes, okay? So those scary yellow glowing eyes, give off light, right? And that light travels in this direction, okay? Does that make sense? angle of incidence equals angle of reflection. If there was nothing there, it would bounce off the wall and it would come back. Or more likely, it would get absorbed by that wall and not bounce anywhere. Does that make sense? Okay. But now, let's say, what color do I want to use? Whatever. Now let's say there's a mirror there. Okay? If the mirror's like that, angle of incidence equals angle of reflection. The angle of incidence is 90 degrees. The angle of reflection is going to be 90 degrees. It goes straight back to the scary demon, and he sees himself in the mirror. Does that make sense? Okay. But if it's all connected. But if we take the mirror and tilt it like this.
Oh, I see what you mean now, because it looks like he's standing in front.
Right.
There.
Angle of incidence equals angle of reflection. Now you see the scary yellow demon eyes, but your eyes don't know that that's a reflected ray. You know what I'm saying?
Yes.
So how does the house work?
That's-
How's the house?
I didn't think about tilting, I thought about tilting.
So, this is true with reflected rays, but it's also true with refracted rays. So here, this ray comes to your eye, but your eye doesn't know that it bent at the boundary. So, if we draw a line backwards
Oh, so the guy thought that it would be right there.
like that, right? You would see, quote unquote, this object here at this position, even though that's not where it is. So if you do ever find yourself in a wilderness survival situation, and then you have to, Yusuf, you okay with that argument? Your face is
Oh, you
suggesting
had
that
to, like,
you're
kill
not.
fish?
Exactly.
You have to kill fish, you have to do it a bit closer.
If you're like, if you see the fish in the water, don't throw your spear at the water or at the fish. Throw it in front of the fish, because that's where the fish actually is. Don't stab your. Well, you probably shouldn't put it that close.
How do you know how much closer?
Well, that depends on you don't, because you're not exactly sure what this angle of incidence is coming to that boundary.
Does all water have the same index incidence?
All water does have the same, well, I guess, sorry, I should probably say that.
Temperature
Like,
doesn't make a
salt water is going to change that a little bit. Temperature will change it a little bit, but not dramatically. All right. You okay there? You okay with that? So, last thing. Okay. Here's a tank of water that has 4 different light rays. And the first light ray goes straight up. If we approach the boundary between the two media at 90 degrees or right along the normal line, there is no bending. The wave will speed up. In this case, it goes from water to air. It will speed up, but it doesn't change the path because it's just going in a straight line. So there is a refractive index, and there is a change in the speed of the wave at that boundary, but it doesn't change direction. Here, you can see refraction occurring. Okay, refraction occurring. All right, and mathematically, there's a reason why this is different than this, and you guys will explore that when we do problems over the next couple of days. But there comes a point that as this ray is coming in, it doesn't refract, it reflects. Because of the way that it's approaching the boundary, the molecular structure allows that reflection as opposed to letting it pass into the next one. Okay? We refer to this as total internal reflection, and I'll show. I have a slide that shows you that here in a second. Okay? So total internal reflection occurs at a certain angle, and we call that angle the critical angle. Okay? So, like we just discussed here, okay? These are different rays of light. Okay? Ray number 1, you guys have this picture actually. I think it's on the last page here. I think it's on the last page. So ray number 1, okay, at the boundary, there is some reflection, but there's also some refraction as well. Going back to that very first picture that I showed you, right? when the light wave hits the glass, there is a little bit of reflection. So at this point right here, we call the critical angle. What happens is that light is refracted along the boundary, or the angle of refraction is 90 degrees because it's along the boundary or perpendicular to the normal line. Any angle past that, we get total internal reflection. That nothing passes. Is everything okay? That we get reflection at that boundary as opposed to refraction. And that leads to something like this. You may have seen this before, okay? Where we get a light rope. If you've ever seen.
Oh, is it you plug in the outlet and this just goes like a chart photon?
Might be it, yeah, actually.
Yeah.
I've never seen that before, but that might be it.
It's like light
So-
so you can find in the dark when you're looking for like this charge.
That might actually be it. So,
But it charges really slow because they use all the like the wire
So- that as this light goes through here, these angles of incidence are greater than the critical angle for this material. And so as it keeps reflecting through the material and comes out the other end. Yes, that's fiber optic
So
cable.
the angle is not strong to keep through the material.
Yeah, generally the bigger the angle is when it approaches this boundary,
It's like weaker, right? Like
it doesn't refract into the other material. But Mahan, yeah, this is a fiber optic cable. That's exactly the principle that the fiber optic cable works under. That instead of sending electrical signals, it sends signals with light. Light travels a lot faster than electricity does, and so those messages get sent faster, and you don't have to worry about frictional losses of electrons passing through that wire because there's no matter that's moving. It's just the light that's moving. Yeah, that's fiber optic cable. So. Yeah, same idea. We're just you're using light. Any kind of like speaker or whatever, you have to send an electrical signal from the source of the sound to the speaker for amplification. And then you send the signal through the wire, and then the speaker amplifies that signal. Does that make sense? But you don't send sound waves through the wire. That doesn't work. Or it could work, but then you're like sending a sound wave through a wire is the equivalent of making a phone out of two cans and a string. You know what I'm saying? That's basically what sending sound waves through a wire would be. But electrical signals are much more efficient than sound waves, and then light waves are much more efficient than electrical signals because you don't have the frictional losses as the electrons move through that conductor. But, so yeah, any system like that, you're sending that signal through the wire, and then the speaker turns that electrical signal back into a sound wave, and that's what we hear. Does that make sense? So fiber optic cable works the same way, or an optical sound cable works the same way, where some source is creating a sound wave, then there's a pickup that takes that sound wave and turns it into a light signal. Then the light travels through the wire to the speaker reads the signal in the light and turns it back into a sound wave. So that's how it works. But with the fiber optic cable, with that optical cable, because it's light, you don't lose as much of the signal through as it travels. So.
Yeah, because like, when I was setting up